So I want to talk about an idea really quickly. I don't want you to get too hung up on this particular idea. It's just sort of a fun process. It's called order reduction. And you might say, well, okay, where have we seen the word order? Well, we talk about like a first order, second order, third order differential equation. It's about how many derivatives you have to solve. And so when we talk about order reduction, the idea is like, well, we want to somehow solve a simpler problem, somehow reduce the derivatives involved. And so the problem is the following. We have a differential equation. It's a homogeneous differential equation right now. It'll stay that way. And we say, okay, we have to solve this. Now, it's a second order homogeneous differential equation, so it's like, all right, we should expect two solutions because the order should be how many solutions you should get out. When I say two solutions, I mean two linearly independent solutions. They say, well, so what if we know y1? So we already have one. We have one in the hand. Can we use it? In other words, does knowing a solution help us to find other solutions? Or does it at least make it a simpler problem? And the answer is yes. Knowing a solution can help us find the other solution by somehow simplifying the problem that remains. So what we want to do is somehow exploit the solution that we have. And so what's the idea? Well, the idea is we say, we're going to make our second solution look in a very particular way. So our second solution is going to be u times y1. Now, when we write u times y1, to be very clear here, we're really talking about y2 of x equals u of x times y1 of x. So in other words, u is this unknown function. And now we say, look, if I want to find y2, we've now changed the problem, and we say, okay, how do we find this u? Well, what do? We say that y2 here is our other solution. So what we want to do is when we have a solution, we have this idea of, well, you verify it by plugging it in. So that's what you do. So you're going to plug y2 into this differential equation. Well, of course, that means you have to know the derivative, which means product rule. You have to know the second derivative, which means a couple more product rules. And you plug it in. So what's happening here in this part, this is our plug in, our y2, and then the other part is to simplify. So a lot of this is something that we don't memorize. It's about the process and it's about what's happening. So we have our second derivative, that's right there, plus a1 times our first derivative, plus a0 times our function, and of course that equals 0. And then we say, all right, you group. So you have the things that involve two derivatives of u. You have the things which involve one derivative of u, which is coming from two places. And then you have things which involve no derivatives of u. So the part that involves no derivatives of u, that's something nice happens. You say, if there's no derivatives of u, it's basically like you were almost treating like u as a constant. It just sort of came along for the ride. And it matches what's up here. You say, look, perfect. But we know since it's a solution, that part goes away. So that's where the phrase reduction comes from. So since this goes to 0, this is our reduction. And now, well, what's left? Well, what's left is a little bit simpler differential equation. Now you might say, and justifiably at this point, you didn't really reduce the order, Steve. Wait, what? Well, you started with the second order. You have a second order. But it's a little bit simpler. In the following sense, when you look at this, what's not there? The answer is u. U's not there. So what you can actually do is to solve for it, you can do, this is one of the things we learned when we talked about substitution, we can say, okay, let's set u prime to be something, we'll call it v. And then you can say, u double prime, u double prime is v prime. And so then what we have is it becomes a 0 equals y1 v prime plus stuff times v. So it really becomes a first order differential equation. And then we solve another first order differential equation. So it becomes a simple process because we know how to solve first order differential equations. I hope, because that's coming up on the exam. Oh, the exam. All right. Now there's a couple of things. There's a few notes here. The first note is to say this will end up giving us the full solution for y. Since it's homogeneous, we can think of it as a complementary solution. And I think we'll see that because we'll do one example. The other note I would really stress, and I think this is true for a lot of the class, is memorize the process. Don't memorize the formula. Because I think it's hard to remember formulas like this. Like I would look at this and like, there's no way I can remember that. But the process I understand. It says, process is put y2 equals uy1 and feed it into the differential equation and see what the new differential equation becomes. That's a simpler process and less likely to make a mistake. You want to keep things simple. That's the goal. All right. Any questions before we do an example to see how this works? Okay, let's do one example. All right. So, verify that y equals e to the x is a solution of xy double prime plus 3 minus 2xy prime plus x minus 3 times y equals 0, and use reduction of order to find a second solution. So, in other words, we have this differential equation. It's not our favorite type. It's not constant coefficient. It's more complicated. It's not even an Euler equation, which we talked about last time. So it's like, how can you do it? So here it says, look, we'll give you one. Okay, so we have to verify. Well, we do whatever we do when we verify, we plug it in. So we have x, and we multiply it by what happens when we take the second derivative of e to the x, plus 3 minus 2x, plug in e to the x, plus x minus 3, and let's just plug in the function. And now we have to think, okay, what's the second derivative of e to the x? Yeah, they gave us a nice function. The first derivative of e to the x is e to the x. And e to the x is e to the x, yes. Good. All right, so we multiply this out. We have x e to the x, 3 e to the x, minus 2x e to the x, plus x e to the x, minus 3 e to the x. And then we just sort of say, okay, things go together. There's the e to the x terms. If you add 3 e to the x and subtract 3 e to the x, what do you end up with? 0. If you have x e to the x, subtract 2x e to the x, and add x e to the x, what do you end up with? 0. So at the end, we get 0. Ta-doo! So that's our verification. All right. Well, that's just the first part. So now it's like, great, we have a solution, but we want the second solution. And I don't think I see any obvious candidates. All right. Well, but we're not going to try to randomly guess. Not today. Instead, we're going to say, all right, let's think about the process. Now, the process says we have one. So really when it says y equals e to the x, we think, that's like y1 equals e to the x. Our first solution is e to the x. And so then we say, okay, great. We're going to set y2 equal to some function e to the x. All right, so we have to find the derivative and the first derivative. So y2 prime. What rule do you use for taking the derivative of u times e to the x? Product rule. Is anyone brave enough to tell us out loud what it is? No? Okay. derivative of the first times the second plus the first times the derivative of the second. E to the x is pretty nice. Okay, and y2 double prime is a similar thing. You would take product rule on each one of these. So on this one, you'd have the derivative of the first times the second plus the first times the derivative of the second. And here you take the derivative of the first times the second plus the first times the derivative of the second. And you might say, ooh, those middle terms, they match up. And you might wonder, is that a coincidence? And the answer is, no, it's not a coincidence. It's actually kind of cool. In fact, if you might notice something about these coefficients, 1, 2, 1, have you ever seen coefficients like that anywhere else? 1, 2, 1? Yeah, like polynomial, like x plus y squared. X squared, 2xy, y squared, 1, 2, 1. Is that a coincidence? No. But that's not our story for today. All right, so we won't go into that part. So we have our pieces, and now we plug it in. So we get 0 equals. So we have x times, and we plug in y2 double prime. So u double prime e to the x plus 2u prime e to the x plus u e to the x. All right, plus 3 minus 2x y prime u prime e to the x plus u e to the x plus x minus 3 times y2 u e to the x. All right. Now at this point, you gather. Okay, so we gather according to the u's. There's a u prime, there's a u double prime. So we gather by those derivatives. So we say, all right, what's happening with u double prime? Do we have any u double primes? Yeah, we have one of them right here. What goes with that? X e to the x. And that's it for u double prime. All right. Then we say, all right, what's happening with our u primes? Well, how many do we have? 2 of them. So for the first one, what's attached to u prime? 2e to the x times x. Don't forget that x out in front. So I'll write that as 2x e to the x. Here, what's attached to u prime? E to the x times 3 minus 2x. Yeah. So plus 3 minus 2x e to the x. Plus u. And what's attached to u? Aha, someone saw the game. They said, Steve doesn't have space to write very much down. Normally he leaves a suspicious amount of space. Here, there's a suspicious amount of space missing. But the point here is this one will always be 0. Because what happens, well, you get the x e to the x, which is what we have here. The 3 minus 2x times e to the x, which is what we have here. The x minus 3 times e to the x, which is what we have there. And we know that that combines to 0. All right, so now we have our differential equation. Well, we can always simplify. Does anything simplify here? Yeah, notice that you could, for example, you could think of pulling out e to the x. You have 2x plus 3 minus 2x. So what does it simplify to? 3e to the x. All right, so we now have that 0 is equal to, all right, as x e to the x u double prime plus plus 3e to the x u prime. Can we simplify again? What? There's lots of discussion. Can you give me a hint of what we're thinking? Yeah, we can divide by e to the x. And this, you can always, dividing by e to the x is always safe because e to the x is never 0. All right. So now we're like, wow. x u double prime plus 3u prime. Okay, well, what can we do? Okay, oh, you really want to do it that way. Awesome, cool. There's something we could have done, but this is great. We'll do v equals u prime. V prime equals u double prime. So then we get 0 equals x v prime plus 3v. What kind of problem is this? It is separable, yeah. Now some people might be thinking like first order linear, Steve. Yeah, you're also right. Everyone's right. Good. Now, when you have options, you always pick the one that's easiest for you. It doesn't mean the one that's easiest for you might not be easiest for somebody else. I like separable myself. So let's suppose we do this as separable. So this would be, we could write it as x dv dx equals minus 3v. So I'm just moving the 3v across. And then move things around, dv over v is equal to minus 3 dx. Oh, yeah, over x. Good, thank you. That was a very dramatic pause. Just checking. All right, now what? You integrate, good. So we integrate both sides. It's good to remember how to do these because, you know, at some point we might have a test. He keeps talking about test a lot, doesn't he? He does. All right. So after we integrate, what do we get? Natural log of v equals negative 3, natural log of x plus c. Now this is the same as log x to the minus 3 plus c. All right. Now what do we do? Raise both sides to the e so we can solve for v. Well, I did not plan well, so I'm going to cram that computation in here. So we get v is equal to what? So we took this left-hand side, e to the log v. That gives us v. What's e to the right-hand side? C times x to negative 3. Yes? Yeah. Now, be careful here. You know, a lot of people are like, oh, shouldn't it be like x to negative 3 plus e to the c, Steve? Like, no. You have to take the whole side. And then people are like, haha, but e to the c is a constant. Now, are we done? No. Because what is v? U prime. So, u prime is c x to negative 3. Well, so what do we need to do? Integrate. Well, so u will be someone was like negative 1, and they're like, oh, Steve's going to do something. Integral of c x to negative 3 will be cx to the negative 2. Right? Now people are like, wow, that is not how integration works, Steve. But that is how constants work. Remember, constants can absorb constants. So normally when you integrate x to negative 3, you'd have negative 2, and then we'd have to divide by negative a half. But then what can we do with our constant? It can absorb that negative a half. All right. Of course, people just looking at the notes without having the context of what we just said are going to be really confused. That's why you come to class. Are we missing anything? Yeah, plus d. Now, we solved for u. That's fantastic. Is this our second solution? And why not? You're right, it's not our second solution. Why isn't it our second solution? Yeah, So remember, our second solution is over here. It's u times e to the x. This is just u. So our real second solution is going to be y2. We multiply u by e to the x. Now, x negative 2 is the same as dividing by x squared. Now, have we seen this before? This d e to the x. Or just say e to the x. It's y1. Remember, there was a note on the previous page that said, when you run this process through, you'll actually have the full complementary solution. And the reason is, you'll get your second solution, and then this extra constant that comes from the integration at the last step also captures your first solution that you already knew about. So this is actually the whole solution. All solutions will take that form. And I'm betting not a lot of people would have guessed e to the x over x squared as the second solution. But we didn't have to guess. There's a process. All right, well, there we go. On to today's topic. All right, so what's for today? We're talking about our favorite kind of differential equation. And 3 keys: constant coefficient, homogeneous, linear. Perfect, perfect. And this is our favorite type of differential equation. We've already talked about this a few days ago. We said, hey, these differential equations, and they have this particular form, some constant number times the nth derivative, some constant number times the n minus first derivative, always just constant times some derivative, added up gets to 0. And the reason we like these is they're really very simple. See, look, all solutions should look like e to the rx. And we say, okay, great. And so what we do is you say, if that's our solution, you plug it in, just like you would if you were verifying. And you say, well, what does that say? Well, it turns a linear differential equation problem into an algebra problem. Namely, it says, look, you're after finding roots of a polynomial. And we've spent years of our life practicing, making our 9th grade teachers proud of how we could find roots. Or maybe our 10th grade. Or maybe if we were held back another year, our 11th grade. But, we're good at this. We're good at this. We know how to do it. And it's really quick to go back and forth. See? You just say, coefficient, the order of the derivative, power of r. And just do. All right. So, we find our polynomial. We find the roots of our polynomial. And then the last thing is to say, how do you find the solutions? Well, it turns out that there's 2 things to worry about. What if you have a real root? Well, okay, if you have a real root, then you look like e to that real root x. Now the problem can be, well, what if it's multiple times? You have the same root over and over. Because you can't just write the same function over and over. That wouldn't give you something new. You always have to get something new. And so the idea is you add powers of x. So if I have a root k times, I want to have k different pieces. And each one of them has to be different. So what you do is you just keep multiplying by your powers of x until you end up with k parts. Now that's if you have a real root. What happens if you have complex roots? All right, so there's a little bit of an aside here. And I know you're like, well, that's not a little bit, but this is really short, actually. So there's this cool fact that says e to the power I theta is cosine theta plus I sine theta. And it's like, what? How is that true? And then you take calc 2 and like, oh, that's why. You can prove this using sequences in series. And it leads you to one of the beautiful facts of mathematics some people consider this like the most amazing equation. If I take e to the pi I and I add 1, what does that equal? It equals 0. And you're like, whoa, e and pi and I, you have 0 and 1. Those are like the two most popular numbers. Adding, like that's really cool. The idea of things being equal. It's like all of the good stuff in math in just one equation. Okay, so anyways, there's a few facts. There's an algebra fact. It says if you have complex roots of polynomials, then they always come in pairs. And we're assuming that all our coefficients are nice, so they're all real numbers. You say, all right, so you have your pairs of roots. How does that translate to solutions? Because we're not used to thinking of complex solutions. And we say, well, hey, our solutions look like e to wherever the root is times x. So we say, okay, it's e to the alpha plus beta ix, e alpha minus beta ix. And we say, all right, now we use the power of polynomials and exponentials and all sorts of things. So the first thing is, you can imagine distributing the x through, and you have addition upstairs, which translates into multiplication. So this would become e to the alpha x, e to the I times beta x. And a similar thing happens on the second term. You say, all right, now let's use our cool fact. So now we can replace this exponential, which has an I in it, in terms of cosine and sine. And we do it for both pieces. So, all right, life is good. And then we say, we know stuff about cosine and sine. For example, sine is a very unusual function. Weird, strange, peculiar. Some people might even say that sine is odd. It's an odd function. Well, what that means is you can have that negative come out. Cosine is an even function, so whether it's negative or positive, you get the same result. And then you do grouping. You have, I have an e to the alpha x cosine beta x and an e to the alpha x cosine beta x. You group those two together, same with the sine beta x. And the punchline is, we went from saying, all right, I have a combination of a and b in terms of an expression, and by rewriting it and grouping, I have, again, some combination, e to the alpha x cosine beta x, e to the alpha x sine beta x, where what you're doing is the c is the a plus b, and the d is the ai minus bi. And this feels more comfortable to us. So, the moral is, if you have complex roots, the real part goes inside the alpha. The real part alpha goes inside the exponential piece, so e to the alpha x. The beta, the complex part, is what goes inside of either the cosine or the sine. Actually in both, so these always come in pairs. So cosines and sines always comes in pairs. And that's basically it. So we know that we translate into a polynomial, we find the roots of the polynomial, we read off the roots, and that gives us our pieces, and then we throw our pieces together. Some constant times our first piece, some constant times our second piece, all the way up into however many pieces we have. So that's the idea. All right. Well, that's the theory. Let's try something. Is there a question? Yes?
Can you repeat what the alpha theta of the complex roots is again?
Well, they're just like numbers, like 1 plus or minus 2i, or 2 plus minus 3i. So
That's like 1/2, a real root of 1/2.
Well, so you might have something like x squared plus 2x plus 2. That's a polynomial. Of course, people believe me when I say x squared plus 2x plus 2 is a polynomial. And if you set that equal to 0, your roots will turn out to be 1 plus I, 1 minus I. So in this case, we would just say, that's 1 plus minus I, and then alpha would be 1, and beta would be 1.
Okay.
All right. Let's just little bit of practice. Here we go. There's a differential equation where the auxiliary polynomial has the following order. So they didn't tell us what the differential equation is. They just said, hey, we found the auxiliary polynomial and we found the roots. And now it's asking us write down the general form for a solution. In other words, what does a typical solution look like? Now, here's the thing. However many roots you have, that's the order of the differential equation. And that's how many pieces we're going to have. You'll notice there's a lot of pieces here. So we're really going to be using up a lot of the alphabet. No problem. Okay, so let's talk about our pieces here. First off, 0. 0 is a fine root. What does a typical solution look like? Well, it looks like e to the 0x. Right? Because it's e to that root times x. Is there another way to write e to the 0x? 1. Yeah, so when you see roots of 0, that means like 1 is a solution. But 0 is a root twice. So we know we're going to have something times 1, but what else will we have? Yeah, we've got to bump up for our next solution that corresponds to a root of 0, so you multiply by x. Okay, so those are our 0 roots. It's a repeated root. E to the 0 is 1, and then you have to bump it for your second time. Okay, then we'll go to 1. Well, that's not repeated, so that's good. What does that look like? What's the function? E to the 1 times x, right? Because it's just no surprise. All right, and then we'll go to our next set of roots. Minus 2's. All right, well, what does that look like? If I have a root of minus 2, what's our function look like?
E to the negative 2x.
E to the negative 2x. But we have it repeated, so what's the next one going to look like? Yeah, we add an x. And then it's repeated again. So what do? X squared, e to the negative 2x. All right. And then we come to 1 plus minus I. All right. Now, here, you can think of it as really 1 plus minus 1 times I, right? Oh, because, yeah, that's true. I mean, no, that's not too surprising. So this is going to involve a sine and cosine term. So 1 plus minus I will give us what type of functions? So whenever you have complex roots, you'll have a pair of functions involving sine and cosine. The real part is the 1. That goes into the exponential, e to the x. Cosine, then you look at the imaginary part, x. And then there's e to the real part, 1 times x, sine, 1 times x. So complex roots come in pairs, and the pairs look like cosine times sine. So you're going to get, it's a little bit hard to see with this one, but the next one will be fun. G, e to the x cosine x plus h, e to the x sine of x. Just imagine if we had some initial conditions. This would be fun. Or not. Probably not. Okay, this might be a little bit clearer to see what's going on. The negative 3 plus minus 2i. What will our solutions look like that correspond to those roots? So you use the negative 3. That tells you what happens with the exponent of the exponential function. And cosine 2x and sine 2x. Okay? So the 3 shows up there. And the 2 shows up over in these pieces. All right. So, what's next? Yeah, plus capital I of e to the negative 3x cosine 2x, and then j e to the negative 3x sine 2x. Are we done? No. We have repeated roots. So now what comes next? Okay? Yeah. And then you bump these. They both get bumped. So x e to the negative 3x cosine 2x plus L x e to the negative 3x sine 2x. And now what? Box it. We're done. Every single root has been accounted for. You got your zeros, 2 zeros, your 1, your 3 2s, your 1 plus minus I, and your repeated negative 3 plus minus 2i. So that's the solution. All right. Well, so somebody asked the question, why can't I just pull one of these out and make it a constant? And the answer is, it might be 0, because it depends on your initial conditions. So you don't know a priori whether it's 0 or non-zero, so you have to leave it in this form. All right, well, I think it's time for you guys to do a problem. Go the other direction. We're going to give you... What? You should be like, sweet, this looks awesome, Steve, thank you. All right. So, find a constant coefficient homogeneous linear differential equation. So in other words, you have to find the differential equation where the solution looks like that. So, C1, C2 e to the x, C3 x e to the x, C4 e to the x, cosine 4x, C5 e to the x, sine 4x. Now, I'll give you a hint before you start. What's the order of your differential equation? And how do you know? 5. It's a 5th order. Why? Yeah, you got 5 constants there. Each piece is in order. All right, so you need to come up with a 5th order differential equation where that's the solution. Now, let's just think about the process. So we have the functions. What can the functions tell us? The roots. Okay, so let's write the roots under each piece. What's this root? 0 here. 1. 1 again, it's a repeated root. And then these combine together to give 1 plus minus 4i. Ah, you guys are great. You already know how this is going to go. Now we have the roots of our polynomial. Well, if you have the roots, you can make your polynomial. So you'll have x minus 1 squared from the 2 1s. And then 1 plus minus 4i, if we only knew a way to find a nice polynomial that had those roots. Oh, there's a note. All right. So this would be x minus 1 squared plus 16. Okay, well, x minus 1 squared, does anyone know that? X squared minus 2x plus 1. Well, it's the same thing here, except instead of plus 1, you have plus 17. Okay, that's supposed to be, say, 17. I know it doesn't look like it. It's just very stylized 17. All right. Well, I can multiply this x through. That's x cubed minus 2x squared plus x times x squared minus 2x plus 17, written like a normal person. And now what do? You expand. X cubed times x squared is x to the fifth. X cubed times minus 2x is minus 2x to the fourth. X cubed times 17 is 17x cubed. Minus 2x squared times x squared is minus 2x to the fourth. Minus 2x squared times minus 2x is plus 4x cubed. Minus 2x squared plus 17, times positive 17 is minus 34x squared. So I'm just multiplying it through. Then I have x times x squared is an x cubed. X times minus 2x is minus 2x squared. X times 17 is 17x. And so I'm doing bookkeeping, but of course it helps to sort of organize your bookkeeping. Organized bookkeeping, you're more likely to make sure you got everything accounted for. So it's x to the fifth. How many x to the fourths do we have? Minus 4x to the fourth. How about x cubed? What do we have? 17 plus 4 plus 1 gives us 22. How many x squareds? Minus 36. How many x's? 17. All right, so that is our auxiliary or characteristic polynomial. So we're almost done. What's the last thing to do? Last thing is just like translate. See, we talked about going from differential equation to polynomial. Polynomial to differential equation is the same thing. So this x to the fifth would become what? Y to the fifth. Or you could write 5. Minus 4 y to the fourth plus 22. Third derivative minus 36. Second derivative plus 17. First derivative equals 0. And then there we go. That's the idea. So the process is not so bad. There's a little bit of algebra, but there's a reason we want you to know algebra. All right, we'll do one more problem to finish the day. This is more of a typical problem, like, oh, so boring. No, come on. But we got to do the routine problems as well. Find the general form for solutions of the differential equation. In here, they use the different notation. So fourth derivative of y plus 8, third derivative of y minus 9, second derivative of y equals 0. All right, so run the process. What do we do first? Turn it into a polynomial, which would be r to the fourth, 8r cubed minus 9r squared equals 0. Well, what can we do with this polynomial? Factor it, find roots. Now, normally it's like fourth degree is scary, except for like, oh, it's not so scary. What can you do with this to start? Yeah, factoring r squared out. So it's r squared times r squared plus 8r minus 9. All right. What are the roots of r squared plus 8r minus 9? Or does that factor maybe? Someone has suggested it's r plus 9, r minus 1. We can always check. R squared minus r plus 9r is plus 8r. And then minus 9 does in fact give minus 9. So the roots are 0, 0, negative 9, 1. All right, let's go through the roots and find our functions. The root of 0 will give us what function? Yeah. A times 1, right? And when we say general form, got to have the constants. The second root of 0 will give us what? B times x. It's been bumped up. The negative 9 will give us what? C e negative 9x. And the 1 will give us d e to the x. And that's the general form. So we don't have to solve for initial conditions. And that It's time.